Hey guys, today I'd like to talk about NMDA receptors. They're the primary excitatory receptor in the brain, meaning that they facilitate the majority of neuronal excitation, the propagation of action potentials. And there's a lot to them. They're very complex receptors. They're ionotropic receptors, meaning that they use ion influx as their method of transmitting a signal into the cell to elicit the biological response, which in most cases is the firing of the neuron. So first of all, just to go over the basics of NMDARs, the primary two endogenous, meaning naturally occurring molecules that are ligands to the NMDA receptors are glycine and glutamate. And they are agonists of the receptor, meaning that they bind to the orthosteric site, illustrated here on the NMDA receptor. And it's considered, necessary for both of them to be bound to elicit a full response of the ion channel pore opening. So right here is just a basic illustration of like the presynaptic and postsynaptic neuron. These illustrate different receptors. Some of them might be NMDA receptors, some of them might not be. And this is the illustration of the NMDA receptor itself. So at resting potential, that is when the associated neuron, this is the intracellular space here, the inside of the neuron, and this is the extracellular space, the outside. So at resting potential, when it is polarized and has a net negative charge due to the presence of anions like chloride, for an electrical signal to fire through the neuron, something called a action potential must be generated. And what that looks like is, is something like this. So this is the resting potential here, and that is a voltage in millivolts, usually between, I believe, 60 and 70 millivolts. So when there's some sort of stimulus, whether it be ions being pumped into the cell, that is cations, positively charged ions like potassium, sodium, this potential rises because you have an influx of positively charged ions, and that depolarizes the neuronal the membrane potential. So this can be considered like a catalytic event. Now, the NMDA receptor itself, even if it has glutamate and glycine bound to it, which I'll just illustrate real quick. Like, let's say that glutamate is bound to the orthosteric site, glycine is bound to the coagonist orthosteric site. Nothing's going to happen here because at resting potential, you have a magnesium or zinc divalent cation that associates within that pore and blocks it. There are like three factors that require the NMDA receptor to channel, the ion channel to open. You gotta have glutamate, glycine, and then you also have to have the removal of this natural antagonist. And when the cell begins to depolarize, that is more positive ions influx into the postsynaptic neuron, like let's just say, for example, potassium and sodium. It drives, it essentially signals the magnesium here to fuck off. So that then allows an influx of calcium ions, calcium cations, which further depolarizes the cell. So you have a lot of calcium, which is a divalent cation, meaning that it has a charge of 2, and you have that flooding the cell because this essentially creates a chain reaction. The more depolarized the cell becomes, it creates the efflux of either zinc or magnesium blocking further pores, and so you have more and more of these receptors opening up and allowing the influx of the calcium. So this process is called depolarization, and on this this little chart that I was drawing, if this is the initiation, then the opening of these ionotropic glutamate receptors would be reaching the threshold in which the action potential spikes, and this direction vertically is more positively charged. This direction downwards is more negatively charged. So once you hit that threshold of depolarization, you get this huge spike due to the chain reaction of the influx of positively charged ions. It creates this electrical pulse essentially that then travels down the axon of the postsynaptic neuron, and then generally you have that quickly repolarize. So this is depolarization, threshold potential, resting potential. Then you have repolarization, and then consequently you have this refractory period where it's more hyperpolarized, and then the return to the resting potential. And the NMDA receptors are, like I said, the most prevalent excitatory receptor. So they're generally used to modulate the firing of neurons, although they're a conditional receptor, since the natural blockade of magnesium and zinc in the ion pore requires several conditions to be met before it catalyzes the chain reaction of the action potential and the neuron firing. So I wanted to go a little bit into antagonism of the well, one more thing I'll mention. There are other both endogenous, meaning occurring within the body, and exogenous agonists that will act at these orthosteric sites. The primary ones are the endogenous ones, glycine and glutamate, but there's also NMDA, N-methyl D aspartate, which is a partial agonist and is less prevalent than glutamate. But they're also exogenous compounds as well. I'm not really going to get into those, but the ones I find more interesting are the exogenous antagonists, and that includes molecules here, like, for example, the aryl cyclohexylamines, bencyclidine and ketamine. And then also you have dextromethorphan and other atypical NMDA antagonists, that aren't aryl cyclohexylamines or derivatives of them. So the way these work is their mechanism is very similar to the endogenous blockade of the receptor that occurs with magnesium and zinc. So let's say we're at resting potential again, primarily negatively charged. The cell is not going to fire, or the neuron isn't going to fire an action potential. Now, if we enter one of these antagonist ligands into the mix, they bind to a site called the PCP site, which is not the exact same location as the magnesium or zinc site, but it is within the channel pore. So they effectively act as a channel blocker. So even if you have glutamate, glycine, or whatever other endogenous ligands agonizing The receptor, it blocks ions from entering the cell physically. It acts as a physical blocker. So if you have secondary activation via ion pumps or something, like you have sodium, potassium being pumped in here through other means, other receptors, other mechanisms of transport. Even if that increases this action potential, I'll just draw another one here, resting potential here, positive, negative. So even if you have these coming in, the influx of cations, it might raise the membrane potential. But the fact that the incredibly important NMDA receptors are being blocked by the antagonist means that there is no chain reaction. There is no explosive increase in depolarization because the cations can't go through and significantly depolarize the membrane. So you have here what would be considered a failed action potential. Different NMDA antagonists are differently efficacious at blocking the channel. For example, PCP is a more efficient blocker than ketamine, and ketamine is a more efficient blocker than dextromethorphan. But so you might have with certain low affinity molecules, like for example dextromethorphan, it induces a partial blockade, but there's still some calcium that is able to enter the postsynaptic neuron, and so it essentially dampens the signal. It reduces the chance of an action potential firing. It reduces the chance that you will hit the threshold potential, which would then initiate the propagation of an action potential. So what does this actually mean, practically speaking? You would think that an NMDA antagonist would be beneficial in the cases of neuronal overfiring, overexcitatory states, as a consequence of some kind of pathology or whatever it may be. And that's true. There are certain NMDA antagonists like memantine or memantine, which will reduce the excitability, but not to a degree that's harmful to the cell. Because when you have too little excitation, certain intracellular epigenetic mechanisms come into play, and it's all about like homeostasis, maintaining a baseline. So when you have either too much or too little of excitation, cation influx, it can cause problems. It can cause neurodegeneration. It can cause cell death. I remember reading an article about chronic ketamine users recently that showed significant atrophy and lesioning in their brains. Mind you, this is a long-term ketamine addicts who used a significant amount. Something I did find interesting was that ketamine addicts who also took other drugs as well, polysubstance abusers, were much more showed much more prolific atrophy than those who just only use ketamine. So it seems that sustained and chronic reduction in the firing of the neurons associated with NMDA receptors, usually by way of exogenous antagonism, can cause lesioning. It can cause apoptosis, cell death. It causes lysing of the mitochondria and vacuolization of the associated neuron. which has been shown in various studies. The topic is a bit contentious because of the disparity of animal and human studies. There have been both human and animal studies that have demonstrated a certain degree of damage to the brain caused by NMDA antagonist toxicity. That's not to say that using something like ketamine at a therapeutic dose is dangerous necessarily. The studies I've seen were regarding ketamine addicts who had been on the drug every day for like years and had been taking over a gram a day, which is like way over, a therapeutic or even a standard recreational dose. So this isn't, I'm not trying to like fear monger here, but it is something to consider. There's very little data on dextromethorphan specifically in terms of long-term abuse and the effects that has on the brain. Like I said, there's the disparity in the animal versus human studies, and as of now, there's no proof, empirical evidence that dextromethorphan causes the same degree of vacuolization, lesioning, and atrophy as ketamine. But it works via a similar mechanism. That is, it elicits its biological response by binding to the same site as ketamine, with lower affinity, that is. I think that's an important subject that needs to be broached and researched, because currently you can't say for sure. I'm kind of going on a tangent at this point. I hope this maybe helped someone have a better understanding of how NMDA receptors work and how NMDA antagonists function. I like to do more videos about pharmacology in general in the future. I'm pursuing a degree in pharmacology with a minor in chemistry. I'm a hobby chemist, and I love studying pharmacology. I've never really made videos about it until now. I mean, as you can tell, this is probably a very unprofessional, shitty video. But you got to start somewhere, and I thought I'd go on and dip my toe in the water and see if it's something that I might enjoy doing. So yeah, I'll talk to you fuckers later. Thanks, bye.